friends to part 2 of this video on correlation and regression. So in the previous video we have discussed about correlation. We have seen different types of correlation like Carl Pearson's correlation coefficient, Spearman's rank correlation coefficient, point biserial correlation coefficient and phi correlation coefficient. We also saw how these things are computed and how we interpret the result from this correlation coefficient. We also discussed some problems of correlation coefficient, that it cannot be used for the purpose of prediction. It cannot tell us the value of one variable if the corresponding value of the other variable is known. Taking a step forward, we go to regression. This video is entirely dedicated to regression. To understand the regression or the type of equation that is to be fit to two variables, we first try and draw a scatter plot. A scatter plot which looks somewhat like this and is actually drawn between 2 points, two variables x and y, may either be in this form or means some of these forms, or there may be several other options as well. The basic thing is that here the values of x and the corresponding values of y are plotted in a graph paper, and they are not connected by any lines, so that we can see a series of points arranging them in different order in the first quadrant or in the quadrant of the graph. And in the coordinate axis we can find out, based on the design in which the points have placed themselves, we can express a relationship between these variables. So this is what we want to see in a scattered plot. And then with the help of this, drawing the scattered plot can be very easily drawn in Excel. So let us go and draw a scattered plot in Excel. So here we come with a, as you can see, there is a data set where we have x and y values, and then let us draw the scatter diagram based on this x and y values. So for drawing that, we actually go to the insert menu, which is exactly here before page layout. Insert menu is already active here, and under insert menu there is an option to insert the scatter diagram. So we click here, then we click on scatter, but before that we first select the data. So we select the data, this x and y data we select, and then we actually click on this option, and then we have different options of drawing the scatter diagram. We take up the first one, and then we see that this graphs comes up. This is actually the scatter diagram where we can see the points. We can change the color of the points as well, we can put here red color, and outline also we make it red so that the graph is more easily visible. So this is we have here these points, as you can see. So these points, if you look at this particular scatter diagram, you see this is x is represented along x-axis, and the y values are represented, that is, these y values are represented along the y-axis. And when we look at the graph, we see that there is a tendency of the points of moving down as the values of x increases. This indicates that the y values decreases as the value of x increases, and this indicates that the correlation between x and y for this case is a negative correlation coefficient. So this is we understand, and also we see that more or less the points are have arranged themselves in a linear fashion, and so we can think of fitting a linear line, a linear equation between y and x. So this is how we draw the scatter diagram, and how we interpret it, little bit about the relationship between the variables, and little bit about the type of equation that may be more appropriate for this type of graph. We can have we can now go back to this presentation, and then we may proceed forward. Now, what is regression? Regression analysis is used for estimating or predicting the unknown value of a variable when we know the value of another variable. That is, very simply speaking, we have an unknown variable, say y, and we have another variable x. So if we can, based on some data available in pairs, that is the values of x and the corresponding values of y, we can establish an equation between y and x, so that if we know the value of x, we can then predict the value of y. So this stage we actually, according to Professor Blair, regression is a mathematical measure of the average relationship between two or more variables in terms of original units of the data. So this is how we define regression. It's a mathematical measure of the average relationship between two or more variables in original units of the data. Let us take up an example to understand it better. So here we have the information about some rats. We have their body weight and we have their corresponding liver. So what we actually want is that we want to predict the value of liver weight given the body weight of the rat, because it is difficult to get the liver weight of the rat. For getting the liver weight of the rat needs to be sacrificed or killed. So we want to avoid this. So we want to predict the value of the liver weight of the rat given the body weight of the rat, and we have some data previously collected, or we have actually sacrificed some rats, and we have found that a rat with 176 gram weight has a liver weight of 6.5 grams. Another rat 176 grams weight but having a liver weight of 9.5 grams. So this way I have many values of this is our x and this is our y. So I want to find out a relationship between this. Say we take an example that a new rat arrives with a weight of 150 grams. So suppose we take up a new rat, its weight is 150 grams, and now can we compute the or can we estimate the weight of the liver of that particular rat without killing this? Yes, we can do that. Here body weight is the independent variable. It means body weight of the rat is the value of x, and the compute the liver weight, which is the dependent variable. Let us establish a relationship between the weight of the rat and the liver weight of its rat, and that is called as regression. But how to proceed with that is the issue here. So let us try to find out how we can use Excel to find out that what is the relationship between variables. So once again we come to this particular example. Okay, so we have this data set here. You see the same data set that we have seen in PowerPoint, that is now copied and pasted in Excel, and let us see how we can extend this diagram and get a scatter plot, and then we fit a linear equation of this. So what we do is that first we come here, we select the data set like body weight and liver weight, we select this, and then we go ahead to insert menu. So we click on the insert menu, and in the insert menu we have different types of scatter diagrams. So we have this scatter diagram. The scatter diagram is drawn, so body weight and liver weight is this. Now we can make the scatter diagram little bit more nice looking by changing the axis. These are some accessories. We click this line, and then we go here, we change the font size, so they look a little bit bold. And then if you want to change the color of the axis, you just click on the axis, and then you format axis option comes before you. There you can go and click here, and line, you can change the color of the line, and it's generally gray in color, but you can convert it to black. You can increase, make it bold also by taking the help of this width, and the corresponding width you may increase, so this looks more vivid. Similar things you can do with the x-axis as well. You can change the color using this color option, and then go to width, and you can increase the width from 1 to 1.5. By default it is 0.75, so it looks nice. Now you see what happens here, that we don't have any rat having a body weight less than 100. It starts at around say if you look at here, 148 is I think is the lowest one, 146 is the lowest one. So instead of starting from 100, you can start it from instead of starting from 0, you can start it from 120. So that will look more reasonable, and there will be no such huge spaces at along the x-axis. So what we do is that we click here, and then the right click, then there is an option format axis. In format axis we can actually have the axis option. So there we can have the minimum value and the maximum value. As you can see, minimum and maximum. So minimum, instead of keeping it to 0, you can bring it to 120. So here you can change it to 120, and then you get this thing. So accordingly you see it starts from 120, and the points gets quite scattered in this way. You can make it 140 also, that will look more reasonable, and this part like empty part will not be there. Here also you can liver weight, none of the rat is having liver weight less than 4, so instead of starting from 0, you can start it to 4. So let me first adjust this, and then instead of 120 let me have 140 here, 140. So it starts from 140, and then let me click here, and then in y-axis options, instead of starting minimum value is 0, but from instead of starting from 0 I can make it like 4. So if I make it 4, then it starts from 4 and goes up to 11, and then the points are very nicely spaced here. Now a question comes that how to get the regression equation, because lever weight is along y-axis, this side is my lever weight. If you want to add a title to the y-axis and x-axis, you may click on this plus symbol over here, and then there are excess titles. So you may click here excess title. So excess title comes up, you may edit it. So this side is the body weight of rats. So you may write here body weight rats, and this side you can make it change to liver weight of rats. And so liver weight of rats. Anyway, so you can make a, if you think that we need to change the color, and also you can go to home, make the color text color black and increase it to 12, and similarly you can do it here, so that makes it more reasonably looking. So we have here the points, we can change the color of the points, like we can go, and then we go to chart tools, format, shape, fill, red, shape, outline, red. So okay, outline gives the all points connected, so make it none, no outline. Okay, so these are how the points look like. They look very nice now. And liver weight of rats, this you can change also to Scatterplot. You may write change the title to Scatterplot between. So we have the graphs here, now. Once we have the graph, we need to fit the equation. So what we do is that click on any one of the points, then you right click, and I repeat this step. Click on any one of the points, left click as usual click. So you see all the points get clicked over here, and then you go to right click this, and then you see there will be add trend line. One option comes add trend line. So you can click on add trend line, and you can get a different types of trend line, as you can see here, out of which you select the linear one, and at the bottom there is a option like and then you press enter, select linear, and then you press enter. Once you do this, then what you get is that below this there is an option display equation on chart and display R square value on chart. So these two, when you click these two, you get the equation and you get the R square value on chart. So this is the how we get the equation. The similar thing, can we have it from here also? Let us have a look whether it is this plus sign provides with an option of adding this. Yeah, there is an option of adding trend line. So just we click on trend line, and then we click outside. So we get the trend line in graph, but we don't get the equation. There is no option of getting equations here. So these points will be estimated by this trend line. So, but then if you want the equation of the trend line, so you click on this trend line, and here there is linear, but below that there are two options like display equation on chart and display R square value. So you click on display equation on chart, so you get the equation there, and you click on display R square value, so you get the R square value there. So now we can bring it outside the graph and make it little bit bigger in font size. Say we make it 12. Okay, so we have the equation there. So you look at the equation, it's 0.0358x plus 1.6498. So 1.6498, this is the called as the intercept, and this 0.0358, this is called as the slope. This is corresponding to the value x. X here is body weight. So y is the liver weight, x is the body weight. And this R square value, as you can see, it's 0.22707. If you let us have these things and try to interpret this. Now we can forget the graph and we can go ahead with these equations. So if you come back to this graph and then we have this. So this is the equation that we have got just now, which you have seen in Excel. So in Excel, the lever weight was expressed as y and the body weight was expressed in x. But we have given it the usual variable name which it should represent. That is, y shall represent lever weight, so we have written lever weight. And x shall represent body weight, so we have written body weight. And accordingly, we have got this equation. Now let us see what is the advantage of getting this equation. Now, along with this equation, we shall represent the values of the correlation coefficient also, so that we can understand what is the strength of the relationship between body weight and lever weight. Relation is okay, but the strength of the relation is expressed by R value or by the value of R square. Now, suppose let us take the example that which we are dealing with earlier, that we have a rat whose body weight was 150 grams and we were trying to estimate the lever weight of the rat. Was it possible? That was the question. So we have now reached an equation. Now we can use this relationship and we can find out the body weight of the lever weight of the rat in the following fashion. That lever weight of the rat is equal to 0.035, which comes from here, multiplied by the body weight, that is 150 grams, plus 1.649, that is 1.649. Now what happens when we replace this value over here, all these values, then we do simple calculation and then we find that the value is equal to 6.99 grams. So that is the lever weight of the rat. So using the body weight, we can estimate the lever weight of the rat. Now this is what we can do with the help of regression, and that is the utility of regression. Now what are response variables? Response variables are nothing but dependent variables. There are different names for dependent and independent variables. Dependent variable is the variable in which we are interested. For example, in the previous one, we were interested in the lever weight of the rat, and that's the reason why the lever weight of the rat was the dependent variable. And we have the corresponding independent variable. The dependent variables are also called as regressed variable, predicted variable, explained variable, or response variable. These are the different names of the dependent variable. Independent variables are called as the regressor, the predictor, or the explanatory variables. In different subjects, these are the words that are being used. For response variables are quite common in medical science or in life sciences as an alternative to dependent variable, and predictor correspondingly for independent variables. Okay. Now let us look at how we can fit equations other than the linear equations. So this is quite simple, and this we can draw from the graph. That means suppose if you look at this equation, if the scatter diagram is like this, or if the scatter diagram points, I can see that the points are quite like this, then this gives an indication of an exponential curves may be fitted to this. Quite similar and little bit difficult to differentiate are logarithmic curves, which also have a similar type of trend, but the fall or the rise is little gradual compared to the exponential curve. So exponential curve rise is quite drastic, fall is also quite drastic, but in case of logarithmic curve, it is just a lagging increase and a lagging fall. So, and if there are so many points arranged in this way, then it indicates a polynomial curve will give a better fit. Polynomial curve means more than having degree more than linear, like quadratic or polynomial of degree 3. It is an expression ax cube plus bx square plus cx plus d. Such curves are called as the cubic curve, or is an polynomial curve of degree 3. So let us go over to Excel once again and try to fit other types of curve in this same data set. So let me have this, let me remove the fitted line also, and now what we do is that we just select any one of the point and then go to this, then comes the add trend line. As soon as we click on add trend line, we have different options that comes up here, like we have exponential, we have linear, we have logarithmic, and we have this, as you can see here, exponential. These are the options that comes up: exponential, linear, logarithmic, polynomial, power, moving average, etc. Now suppose I want to have an exponential curve, so what I do is that I click here, then I come down and then I click on display equation on chart, display equation on chart, and display R square value. So we may remove this line this time. So anyway, so we have this, then we click on this, and then we have here you can click on this graph. Sorry. Okay, here we can take away this. Okay, trend line we have taken away. Fine, then we click here, we go to this add trend line. So it comes here, then instead of linear we go to exponential. So this is the exponentially fitted curve, and then we can have this as display equation on chart and display R square value. So we have this equation, you see, this equation is the equation. Let us increase its font size a little bit so it is visible. So this is 3.4273 into e to the power 0.0047 x. So this is the exponential curve and the corresponding R square value. The R square gives us an idea about the strength of the regression. If you see, if we go to the fit a linear curve, then the R square value is different, and if you fit an exponential curve, the R square value is also different. Now higher the R square value, better is the fit. So if an exponential curve has better R square value than the linear curve, then we should go ahead with the exponential curve. Let us see fitting other types of curve. Let us delete this. Once again we click here, and then we have add trend line. So here we go with, say, we go with a polynomial of order, say we have order 3, and then we have display equation on chart and R square value. So you see, this is the, you can see in the graph, we can remove the linear one. Let us delete, and so we have this equation. You see this curve, this band curve, this is the fitted curve to these points, and this is the equation of the curve. R square value, earlier it was 0.22, now it is 0.28, indicating that this curve is a better fit compared to the exponential curve. So this curve will give better estimate compared to the curves that we saw earlier. So this way we can fit other curves than the linear curve using Excel. So if you go back to the presentation, so we had already seen this. Now we had tried several types of curves, like linear we have already seen, exponential we have seen. We have also fitted a logarithmic curve, and we have fitted a quadratic curve, which we did not see. We see a third degree polynomial or a cubic curve. So we have got these equations. So these equations, and we have also noted the corresponding R square value. Now if you look at the R square value, this value is 0.022 linear. Exponential is even poorer than the linear because it's only 0.216, and then logarithmic curve is 0.231. That means not much of an improvement. Quadratic curve is 0.283. So out of these curves, none of them fit it good, because R square value range is from 0 to 1. So closer to 1 indicates a very good fit. None of them have given a good fit, but out of the 4 poor performers, this is the lesser debit. That means these quadratic curves gives us a better fit. So this is called as the, this is how we can find out that we can compare between different fitted curves, and we can find out that which curve is giving better results. So this is the way in which we can actually compare between the different curves and find out the best fitted curve for a given data set having two variables, one dependent and one independent variable. Now let us look at this interpretation of R square. We have already explained. We can compute the expected values of these from the equation of expected values of lever weight given the body weight. The difference between the actual body weight and the expected body weight from the equation is called as the residual. It is better to draw the residual plot, which is a scatter plot between the residuals against the body weight, that is independent variable. A good fit will show no trend or pattern in the plot. So let us go over to Excel and find out the expected values from the equation, find out the residual and draw the residual plot. This is something interesting we can do, and then we can understand whether the fit has come out to be good or not. So let us go to Excel here. So we have come back to Excel, and let us get the equation. Let us close this, okay, and we have this equation. So let us go to the simple linear equation. So we once again delete all these things, and delete the fitted line also, and then let us see that linear curve. Let us fit the linear curve. So we click here, and then we click on add trend line, and then we go to linear, and then we come down display equation on chart. So we have got the equation on chart. So you can see this is the equation that we have got. Let me increase the font size to make the thing which looks like this. So we have got the equation on chart. Now we can have this equation, and then now let us try to estimate the value. So body weight is x and lever weight is y. So let us write the equation here that body weight this is lever weight, this is equal to 0.0358 then into body weight plus 1.6498. So this is the what we have. The lever weight, body weight, and then 1.6498. This is we have the lever weight and body weight. So once we have this lever weight and body weight, now we can find out the equation. How we can find out the equation? We first write equal to, then we write 0.0358 into body weight. So body weight is this plus 1.6498. So this is the constant, that is the intercept, and then we press enter, and so we get this is the estimated value of the lever weight. Let us increase the font size of the entire thing so that this is comparable. Let me take it to 14. So we have this, we can center it out so that we have this. Now what we do, we don't need to give the formula for all the values. Rather we can click and drag, and using this equation, these are the estimated values of the lever weight of the rats. So 176, this estimate will remain the same, 7.9, 190, then this is the corresponding body weight 190, estimated lever weight is 8.45, actual lever weight, this is the actual value. So now if you go here and have a look at this, so the difference between actual body weight and the expected body weight, this should be lever weight. The difference between actual lever weight and the expected lever weight from the equation is called as the residual. So actual, so going back, actual minus expected. So actual minus expected, that is residual. So residual, we write here residual. Residual actual minus expected, so equal to, so this is the actual lever weight as you can see here. Okay, so actual lever weight, we can have a little bit of the actual lever weight here. So actual is this one, actual minus expected. So actual minus expected. So let me increase the font size a little bit so that these things are easily visible. Actual minus, this is the corresponding expected value, so this is the residual. So we have residual, some of the residuals will be positive, some of the residuals will be negative. So these are the residuals. So when the residual is negative, that means this is been overestimated, lever weight is been overestimated. When the residual is positive, it means that the lever weight is underestimated by the regression equation, that is this. Now if we have a graph between the body weight and residual, then this is called as the residual plot. Once again a scatter diagram. So let me delete the previous scatter diagram that we have, and let me hide this column. So click here and then click on hide. So hide this column. So body weight and residuals come together. So we select them and then we draw a scatter diagram. Insert, and then we have scatter diagram here. Let us have the scatter diagram. So you see this scatter diagram looks very haphazard, and we can once again adjust the axis to have it like it's residuals. So residual, this x-axis values, we can have it till from 140. So I have the x-axis here. I go to format axis, and then minimum value I make it 140, 140, and I press like here you can see I have made the change. Minimum value is 140, and then I click on enter. So when I click on enter, this 140, I click on enter. So this becomes automatically, it starts with 140. Now you can see the points. Let me give a different color to these points. Like I can have a color which is quite visible, like I can have dark blue, not dark red, because dark red was already used. Now you see, and these are the scatter plots, and they look in a very haphazard fashion. There is no particular trend for a particular value of x, that after x reaches a particular value 170, then there is a clear trend. No, but it is at the top also, at the bottom also, so everywhere it is scattered. So this gives a rough indication that the fit is reasonably good, and there is no trend or pattern available with this. Also you can have a look at this. For example, if we select this data and arrange them in particular order, say you go to home, and then in the home tab, and there is a sort button like this. So filter, sort from smallest to largest. Do you want to expand the selection? Yes, expand the selection, and then you have a look at the values, like you have this. So you see, if you feel that there is a potential, like if there is body weight is positive and negative should be mixed up thoroughly, like positive, then negative, then positive, then negative. So they are thoroughly mixed up, not like some positive values in one side and negative values in one side. This gives an indication that the residual plot is supporting your fitted model, because there is no trend in the residual plot. And so far as the residuals are concerned, even if you change the values, if you put the values in ascending order, that is the independent variable, then we don't see any significant trend available in the dependent variable, that is the residual. So that is how we interpret the residual plot, and indicate that the fit is relatively good. So this is where we come and this presentation on regression. So we had seen earlier correlation, different types of correlation, some lesser known correlations like point biserial correlation we have also seen, and we have also seen about the phi correlation coefficient. Here in regression we have seen what is linear regression, how to fit a linear regression using Excel, how to get the equation, how to get the R-square value and interpret it, and then how to fit a regression other than linear regression in Excel between two variables, and then to compare them and find out the best fit. At the end we have seen drawing the residual plot and how we can understand the goodness of fit of the particular curve or straight line from the regression, from the residual plot. So thanks for watching this video.